Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi and today we are going to discuss about the module Cantilever from the paper Semiconductor Materials and Devices. So after completing this module, the students will be able to understand the theoretical background of the cantilevers and its type. Then we will be discussing about the shear force and the bending moment and the natural frequency of the cantilever with tip mass and without tip mass. So before moving further, let's discuss about the cantilever. So the major challenge for the 21st century is to develop the self-powered system, especially those which can be operated using energy harvesters as electrical power sources, which was governed by Jones et al. In 2001. So the self-powered devices are used in the wide range of wireless applications ranging from encapsulated implants to industrial process monitoring. Furthermore, the increasing demand of wireless sensor devices and networks in mobiles and the recent advent of the extremely low power operated electrical and mechanical devices makes such energy harvester sources very attractive. So the traditional power sources such as batteries have various limitations in the current wireless remote sensor systems, which include very large volumes, limited lifetime contribution to the environmental pollution and huge maintenance requirements. So, exploring the possibilities of renewable, sustainable and green energy sources and to replace the fossil fuel is one of the most significant and challenging issue in the energy research. So, a number of ambient sources such as sunlight, heat, magnetic energy and mechanical vibrations have been studied for generating useful electrical voltage. So among them, mechanical vibrations are the most promising and are independent of the weather conditions, which offer great potential in various applications such as energy harvesters. So for harvesting mechanical energy, piezoelectric cantilevers are the promising and excellent candidates. So let us discuss about the cantilevers in detail in this module. Let us discuss about the cantilevers first. A structural element anchored at one end to a support and subjected to a load transverse to its axis at the other end is known as a cantilever. A cantilever is classified under a broader category of beam, and in general a beam can either be free from any axial force or the effect of this force may be negligible. Usually a beam is considered in horizontal direction and load in vertical direction. The load can be of two types. One is concentrated load and the another one is distributed load. The concentrated load is assumed to act at a particular point, though in practice it may be distributed over a small area. On the other hand, the distributed load is the one which is spread over the length of the cantilever. However, the rate of loading may be uniform or may vary from one point to another. And there are different types of support for beam which are as follows. So the first one is roller support. So students, you can see the figure for the roller support. In case of roller support, a beam rests on a sliding surface like a roller or a flat surface. The roller support can sustain a force normal to its surface as well as the possible movement on the supporting surface, which does not allow any resistance at that direction. Therefore, the reaction R along the rolling surface is 0 and it is present only normal to the surface, which is shown in the figure. Now the next support is hinged support. So the schematic for the hinge support is shown, and in case of such support, the possibility of translational displacement of the beam is 0. However, the rotation is possible. In this case, there can be reactions in vertical as well as in horizontal direction. So for the vertical direction, the reaction is represented by R, and in horizontal direction, it is represented by H. The next support is the fixed or encaster or built-in support. A built-in rigid support which does not allow any type of movement or rotation is called fixed or encaster support. A fixed support exerts a fixed momentum, that is M, which you all can see in the figure, and a reaction which is represented by R on the beam. So a beam with one end fixed and the other end free is called cantilever, and there is a vertical reaction R and a moment M at the fixed end and is called the fixed moment. So in the present module, the cantilever beam is made which is supported from one end, that is fixed support, and free from the other end. In this case, the cantilever beam transfers the load to the rigid support where it manages the moment of force as well as shear stress. So here comes shear force. What is shear force? So shear force is one of the most important parameter in case of cantilever. It is an unbalanced vertical force on one side, that is the other than the fixed support of the cantilever beam, and it is the sum of all the normal forces. So in other words, it represents the tendency of either portion of the cantilever to slide or shear laterally relative to the other. So the shear force is considered positive when the resultant of all the forces to the left of a section is upward or to the right downwards. Bending moment. The bending moment is another parameter of interest while understanding the theory behind the cantilevers. Bending moment at some section of a beam is defined as the algebraic sum of the moments about the section of all the forces on one side of the section of the cantilever. Natural frequency of cantilever. So students, in this section, the natural frequency of cantilever having a tip mass at the free end has been calculated, followed by the frequency calculations of the cantilever with distributed mass. Subsequently, the frequency of the cantilever with distributed mass and tip has also been shown. So students, you can see in the figure shown in the middle of the slide. So figure A shows the cantilever beam having mass mt mounted at its free end, that is the tip mass mt, where tip mass is much greater than the mass of the cantilever. Whereas the second figure shows the cantilever beam having the mass m, or you can say the mass is uniformly distributed, so it is represented by small m. Now consider a cantilever beam having a tip mass mt mounted on its free end, which we have seen in the previous slide. Assume that the end mass mt is much greater than the mass m of the cantilever. So a free body diagram of the cantilever system is also shown in the second figure in the previous slide, where E is the modulus of elasticity of the material of the cantilever, I is the moment of inertia of the cantilever about the fixed support and normal to its surface. L is the length of the cantilever, G is the acceleration due to gravity, mt is the tip mass mounted at the free end, R is the reaction force and Mr is the reaction bending moment. So applying Newton's law for static equilibrium, the algebraic sum of rotational force, that is phi f, and the translational force, that is gamma f, must be 0. Therefore, the equation becomes summation phi f plus gamma f is equal to 0. So it becomes R minus mg is equal to 0, which implies R is equal to mg. Also, the algebraic sum of the rotational moment phi m and the translational moment lambda m must be 0. Therefore, at fixed end of the cantilever, summation phi m plus lambda m is equal to 0. This implies Mr minus Mgl is equal to 0, as gamma m is equal to Rl, which is equal to Mgl, as R is equal to Mg. So the equation becomes Mr is equal to Mg into L. Now consider the vibration of cantilever of length L about the fixed end and due to tip mass mt present at the free end. Under dynamic equilibrium, the cantilever is expected to vibrate with its natural frequency, that is Fn. So to determine the value of natural frequency, consider a small segment of length x of the cantilever and starting from the fixed end, which is shown in this figure. Let the tip mass mt in the cantilever results in deflection y at a small distance x from the fixed end of the cantilever beam. Let capital M be the moment due to the motion of the cantilever segment. Then the algebraic sums of the moments at a distance x from free end of the segment is given as summation phi m plus lambda m is equal to 0, which gives mr minus rx minus m is equal to 0. Here lambda m is equal to rx, phi m is equal to mr minus m. So we get m is equal to mr minus rx. The moment m and the deflection y is given as m is equal to ei y double prime, where y double prime is the acceleration of the segment at distance x from the fixed end. Now substituting the moment m in equation number 3, we get ei y double prime is equal to mr minus rx, which gives ei y double prime is equal to mgl minus mgx using equation 1 and 2. So we get y double prime is equal to mg by ei into l minus x. Now integrating the above equation, we can obtain the velocity of the free end of the segment as y prime is equal to mg divided by ei times lx minus x square by 2 plus a, where a is the constant of integration. Now again integrating the above equation further, we get the displacement of the free end of the segment as yx is equal to mg by ei times L into x square by 2 minus x cube by 6 plus ax plus b, where b is also the constant of integration. Consider the boundary condition of the segment at the fixed end as y is equal to 0 at x is equal to 0 means 0 displacement, and the next condition is y prime 0 is 0, that is 0 slope at x is equal to 0. So we get b is equal to 0 as well as a is equal to 0. Now the resulting deflection equation is given as yx is equal to mg upon ei times L into x square by 2 minus x cube by 6. Now the deflection of the cantilever of length L at the extreme free end is given as mgl cube divided by 3ei. According to Hooke's law, for a linear spring, The restoring force corresponding to a displacement y from the mean position is given as F is equal to ky, which every one of you must be knowing. So where F is the stiffness constant. The direction of force is not considered in relation to the convenience, since the force at the free end, that is x is equal to L, of the cantilever is mg. The stiffness constant using equation 8 is given as k is equal to 3ei divided by L cube. The natural frequency Fn of a single degree of freedom system, such as a cantilever, is related to the stiffness K and the mass m. So the natural frequency is 1 upon 2 pi root k by m. Note that the mass term m is simply the tip mass of the free end of the cantilever. Therefore, using equation number 9, the natural frequency of the cantilever becomes F is equal to 1 upon 2 pi root 3 ei by ml cube. Now the next is natural frequency of cantilever without tip mass. So in the present case, the mass is uniformly distributed and there is no tip mass present. Let us now consider a cantilever beam having ρ as mass per unit length as shown in the figure, which is shown in the next slide. We assume that the cantilever has a uniform cross-sectional area and the natural frequency and the effectiveness of the cantilever, that is without tip mass, is determined, where the default mass is represented by the discrete end mass. So students, you can see the schematic of the cantilever having ρ as mass per unit length. So as discussed in the previous case, consider the segment of a cantilever of small length x from the fixed end and having a displacement y towards the normal to cantilever surface at distance x. The governing differential equation of the segment cantilever is given as minus ei del to power 4 by del x to power 4 is equal to rho times del square y by del t square. Now the boundary conditions at the fixed end x is equal to 0 are y is 0 at x is equal to 0. First derivative is 0 at x is equal to 0, means these two boundary conditions are at the fixed point. Now the boundary condition at a free end, that is x is equal to L, of the cantilever is given as del square y by del x square and del cube y by del x cube. All of them comes to be 0, that is 0 bending moment and 0 shear force. The quarter cosine wave solution of the equation is given as y of x is equal to y naught times 1 minus cos of pi x by 2l. So the first derivative for the above equation becomes dy by dx is equal to y naught pi by 2l sine of pi x by 2l. Similarly, the second derivative and the third derivative are y naught pi by 2l whole square cos pi x by 2l, and similarly the third derivative is minus y naught pi x by 2l whole cube times sine pi x by 2l, where y naught is the displacement of the cantilever at the free end, that is x is equal to L. Now it is important to note that the given equation or solution meets all the boundary conditions except for the zero shear force at the free end of the cantilever. So despite the failure of quarter cosine wave solution to satisfy zero shear force condition at x is equal to L, it is accepted as an approximate solution in order to describe the deflection of the cantilever. So the Rayleigh method is used to find the natural frequency of the cantilever with the distributed mass, that is without tip mass. The total potential energy P of the cantilever is given as P is equal to EI by 2 integration 0 to L times d2y by dx square whole square into dx. On solving this equation, we get P is equal to 1 by 64 pi to power 4 EI by L cube times y naught square. So the total kinetic energy T is given by 1 by 2 rho omega square integration 0 to L y square dx, where omega n is the angular resonance frequency of the cantilever beam. On substituting the value of Yx using equation number 12, we get the kinetic energy T as 1 by 2 rho omega square integration 0 to L times y naught 1 minus cos pi x by 2L whole square dx. So the simplified version of T is 1 by 4 rho omega n square y naught square L into 3 minus 8 by pi. Now equating the potential energy and the kinetic energy, we can obtain the natural frequency Fn of the cantilever with the distributed mass. So on equating the potential energy and kinetic energy, we get the expression for omega n square, which is equal to pi to power 4 EI by L cube divided by 16 rho L times 3 minus 8 pi. So the frequency or the natural frequency of the resonating cantilever is given as 1 upon 2 n times 3.664 by L square times EI by rho. The effective mass M effective at the end, that is x equal to L of the cantilever without any tip mass, can be found using equation 9, 10 and 20. Now the effective mass, that is M effective, is equal to K upon 2 pi Fn square, where K is 3EI by L square, which we have already derived. So the expression for M effective is 0.2235 rho L. Now let us compare the natural frequency of the cantilever with the practical cantilever. Consider a practical cantilever beam where both the distributed mass and the end mass are significant. So the total mass Mi of the practical cantilever having tip mass Mt and distributed mass M at the free end is M1 is equal to M effective plus Mt. M1 is equal to 0.2235 rho L plus Mt. Finally, the resonating frequency of the cantilever comes out to be F is equal to 1 upon 2 pi integration 3EI upon 0.22335 rho L plus M times L square. So students, let us now summarize what we have learned in this module. So first of all, we have read that the piezoelectric cantilevers are the eligible and the most promising candidates which can convert the mechanical energy into the electrical energy very efficiently. So the cantilevers, we have read that they are defined as the structural elements anchored at one end to a support and subjected to the load transverse to its axis at the other end. So usually a beam is considered in the horizontal direction and load in the vertical direction. We have discussed that the load can be of two types. One is the concentrated load and the second one is distributed load. So on the other hand, we read that the distributed load is the one which is spread over the length of the cantilever. However, the rate of loading may be uniform or may vary from one point to another. So there are two major forces which are acting on the cantilever. One is the shear force and the another one is the bending moment. We discussed that the shear force is the one which is unbalanced vertical force on one side of the cantilever beam, and this one side is the side other than the fixed support, means the moving side, and it is the sum of all the normal forces, whereas the bending moment is the another parameter which is very important in understanding the theory of the cantilevers. So the bending moment at some section of the beam is defined as the algebraic sum of the moments about the section of all the forces on one side of the section. Then we have derived the expression for the natural frequency of the cantilever having the tip mass at the free end, and the similar study has been carried and understood for the cantilever without tip mass also. Thank you.